All right. So today we're going to be looking at May-June 2024, paper 23. Okay, that's paper 2, variant 3. The first question is explain the lack of reactivity of nitrogen gas. We've done this before, right? Nitrogen has a strong triple bond and it is non-polar, right? That's why it's unreactive. Okay, so strong nitrogen triple bond, right? And the molecule is non-polar. Okay. Remember, generally speaking, the stronger the bond, the less reactive. Okay, and the more polar a molecule, the more reactive it is. Covalent bonds can be sigma bonds or pi bonds. Complete table 1.1 to show the number of sigma and pi bonds in a molecule of nitrogen and to describe how the orbitals overlap to form these bonds. Now, a sigma bond, remember, any two atoms will always, any covalent bond will always have one sigma bond, whether it's single, double, or triple. It's always going to be one sigma bond, right? Single bond is only sigma, double is sigma and pi, triple is sigma and two pi bond. एक sigma हमेशा होगा. You will always have one sigma and exactly one. So between two covalently bonded atoms, right? So you have one sigma bond and then we have two pi bonds, right? Because you have a triple bond. So we have one sigma bond and we have two pi bonds. And in the sigma bond, what happens? The orbitals overlap head on, right? Orbitals overlap head on, also known as a direct overlap. Okay. And in a pi bond, the orbitals overlap sideways. You can also say lateral, means the same thing. Lateral overlap. And I like to say that I also like to always mention that it's only pi bonds apply to only p orbitals, right? Right. Where sigma bonds apply to s orbitals, p orbitals, hybrid orbitals, all of them. Okay. A sample of aluminum reacts with an excess of chlorine. State the oxidation number of aluminum in the product of the reaction. Aluminum is in group 13. Okay. Aluminum is in group 13, right? Which means that it'll always have an oxidation number of +3 in its compound, right? This is the rules from rules for oxidation numbers that we've learned from redox. You should know that aluminum and chlorine react together to form AlCl3. Aluminum is +3 over here. Okay. So the oxidation number is +3. State what determines the maximum oxidation number. Maximum oxidation number is just the number of valence electrons for a period 3 element, right?
सर सबके लिए ये होगा या फिर सिर्फ पीरियड 3?
Period 3. Separate samples of aluminum oxide and phosphorus 5 oxide react with an excess of NaOH at room temperature. Give the state of aluminum oxide and P4O10 at room temperature. They're both solids at room temperature. Okay. They're both solids at room temperature. Write an equation for the reaction of each oxide with an excess of NaOH at room temperature. Now, if you guys remember, aluminum oxide, it says excess NaOH, right? Aluminum oxide initially forms the precipitate aluminum hydroxide, right? Which then dissolves to form this ion, AlOH4 minus, right? Aluminum oxide is amphoteric. It can react with acids or alkalis, right? So it dissolves in excess alkali. Initially, if you add a little bit of alkali, you get a white precipitate, but in excess, it dissolves, okay, to form AlOH4 minus. So for the equation, we have Al2O3 plus NaOH plus H2O gives you NaAlOH4, right? This is your anion, AlOH4 minus, and this is your cation, right? Sodium, Na plus, okay. And then to balance this, we're gonna have 2, 3, 2, okay. And P4O10, okay, reacts with NaOH, sorry, reacts with NaOH to form salt and water. Right now, it's phosphorus 5 oxide. Okay, it's phosphorus 5 oxide. So the salt it forms as the phosphate 5 anion, PO4 3 minus, right? Phosphorus 5 will form phosphate 5. Okay, phosphorus 5 oxide will form phosphate 5. So that will be sodium phosphate, Na3PO4. Okay, again, phosphate is 3 minus, right? This phosphate, this is called the phosphate 5 ion. Okay, so we have Na3PO4 and then we have H2O, right? Again, it's an acidic oxide, so it's a acid-base reaction here, okay? And you're getting salt and water. And then to balance this, you have 4 phosphorus on the left. You're going to have 4 of these. You're going to have 12 NaOH, and you're going to have 6 H2O, right? 4 of these because you have 4 phosphorus. Then you have 3 times 4, which is 12 sodium, so 12, and then you have 12 hydrogen, that would be 6 H2O. Okay. If you forget the balancing, you can always balance it. But just good to remember the period 3 equations because you're expected to know them. The oxide of silicon reacts with calcium oxide in an addition reaction. Addition means they just combine to produce calcium silicate. The oxidation number of calcium is +2. Okay. Reduce the oxidation number of silicon. Okay, so remember group 2 elements are always +2. And remember oxygen is always -2 unless it's bonded to fluorine, right? In which case it can be positive, right? But otherwise it's always -2, right? Oxygen unless it's bonded to fluorine because it's the second most electronegative element. So if we have calcium, which is +2, let's say silicon is X, we have 3 oxygens -2, right? That's the oxidation number of oxygen. Overall is 0. Okay. Overall is 0 over here. So we end up getting X -4 is equal to 0. So which means X is equal to +4. So the oxidation number is +4. Okay. I mean, if you want to write it like this, it's also fine because that's the way they've written it in the question, right? Is a Roman numeral, but I just write it like that just because they've given it that way. But honestly, either way is fine. Calcium oxide can be made from calcium carbonate in a single step reaction. Identify the type of reaction that occurs. So calcium carbonate, you want to make calcium oxide from calcium carbonate. So calcium carbonate is decomposing thermally, right? Thermal decomposition means when you heat it and it decomposes. So form calcium oxide and carbon dioxide. So it's thermal decomposition. Nitrogen reacts with hydrogen in the Haber process, as shown. Table 2.1 shows different conditions used to produce 3 equilibrium mixtures A, B, and C. Describe and explain the change, if any, to the percentage yield of ammonia gas produced in B compared to A. So we're comparing the yield. What's the difference between A and B? Same molar ratio initially, same temperature, same pressure. The only difference is the catalyst. Does the catalyst affect yield? No, right? A catalyst does not affect yield, which means that it only affects the rate. It's going to be produced faster, but you're going to get the same amount. Okay, so you can say that the yield will be 58% yield in B, right? Yield is unchanged, right? Since a catalyst has no effect on the yield. Okay? A catalyst has no effect on the yield. Okay? Catalyst over here being iron, right, in the Haber process. Describe and explain the change, if any, to the percentage yield produced in C compared to A. Okay, the difference in C is that you are using a higher temperature. Everything else remains the same. Pressure remains the same. No catalyst present, right? So we have an exothermic reaction. This particular equilibrium, you should just know from memory, okay? Because they don't even have to mention that it's exothermic. You should know that the Haber process is exothermic, right? And the temperature is a compromise between rate and yield. What that means is that the higher temperature gives you a faster rate, but a lower yield. Why is it a lower yield? Because the increase in temperature favors the endothermic direction. So you'll get lesser product. lesser product, because lower yield means lesser product is going to be formed, right? So again, forward reaction is exothermic, negative enthalpy change. That means backward is endothermic. Higher temperature favors endothermic. Why? Because higher temperature, uh, if you increase the temperature, that extra heat will be absorbed by the endothermic reaction, right? Extra heat needs to be absorbed. Extra heat needs to be absorbed. Endothermic reactions absorb heat. So the reaction shifts to the left, which means your product goes down. So your yield decreases. Okay. So we can say that the percentage yield will be lower in C, right? And the reason why is higher temperature. I'm just going to give you the full explanation, right? Higher temperature favors the endothermic direction. Yes, more reactants will be produced. Higher temperature favors the endothermic reaction, endothermic direction, hence the equilibrium will shift to the left. Okay. Right. Again, remember Le Chatelier's principle, right? If you increase the temperature, the system will react, or the system will shift in a direction that opposes that change. You want to bring the temperature back down. You want to bring the temperature back down, right? So you want to absorb the excess heat, right? The equilibrium will shift to the left to oppose the increase in temperature. Okay. You should always mention the statement to oppose whatever change you made. You increase the temperature, you want to oppose it, right? So the equilibrium will shift to oppose it. So always say that. You increase concentration of a product, for example, equilibrium shifts left to decrease the product, right? That opposes the increase in the concentration. They won't always require this in answers, but it's always good to say it. Okay. Describe and explain the change to the rate of the forward reaction that occurs to establish the equilibrium in C compared to A. You do not need to refer to the Boltzmann distribution. Okay, so we need to just talk about the rate, like just the effect on rate, right? Now, it says the rate of the forward reaction. We know that the equilibrium is shifting to the left. We know that the equilibrium is shifting to the left. But what's happening to the rate? If you increase the temperature, rate always increases, right? Rate always increases. The forward reaction की rate भी बढ़ी है, backward की भी बढ़ी है, right? So the reason the equilibrium shifts to the left is because the backward reaction increases more. They both increase. Forward reaction rate increases and backward reaction rate increases, but the net changes to the left because backward increases more. Okay. So temperature will always increase rate. It's a matter of which rate is increasing more. Is it forward or backward? Okay. So in this case, forward reaction rate will increase. Okay. So we're going to say that the rate of the forward reaction increases. Okay, backward also increases by a greater amount, but we don't really talk about that here. Rate of the forward reaction increases, right? Why? Because as temperature increases, right, you have more collisions, right, or more collisions or particles, or let me say this right. Let me say this properly, right? When you increase the temperature, right, the speed and therefore kinetic energy of the particles increases, right? Hence, you have more collisions, okay? Hence, more collisions or particles, okay, with energy greater than or equal to the activation energy, okay? With energy greater than or equal to the activation energy, right? Yes. You're gonna have more particles with, it says Boltzmann distribution, not particle theory. You have to mention particle theory. Boltzmann distribution has got to do with area under the curve and all that stuff. Particles, though, you don't have to link it to the Boltzmann distribution. This is, did you not learn this in O levels? This theory. O लेवल में बोल्ट्जमैन डिस्ट्रीब्यूशन थी क्या? It's got nothing to do with Boltzmann distribution. The particle theory is just particle theory. Yes, you did learn it in O levels, right? Which means O level में तो था ही नहीं Boltzmann distribution का, कोई Boltzmann distribution से ताल्लुक ही नहीं है. Boltzmann distribution को हमने इससे derive किया, particle theory से. You're thinking about the other way around. This is not Boltzmann distribution. Boltzmann distribution is a representation of what's happening, right? But you have to explain it without referring to that graph or distribution. Okay. So you have more particles or collisions with energy greater than or equal to the activation energy. Hence, the rate of the reaction increases, right? Which you already mentioned. Hence we can say, hence the frequency of successful collisions or effective collisions. Okay, I mean, they use the word effective in the syllabus, so I'll just go with that. Frequency of effective collisions increases. You can say successful collisions as well, it's the same thing. Write an expression for the equilibrium constant Kp. Okay, Kp is for the partial pressures, right? Partial pressures of, again, it's products over reactants. So you're going to have ammonia squared divided by hydrogen cubed times nitrogen, right? To the power of the coefficients. Okay, so ammonia to the power of 2 divided by H2 to the power of 3 times N2 to the power of 1. So we can say partial pressure of ammonia squared divided by the partial pressure of H2 cubed times partial pressure of nitrogen. What are the units going to be? Okay, let's see what the units given are. They've given us the pressure in atmospheres. So we're just going to stick to the units given in the question, right? So in the numerator, we have pressure squared. In the denominator, we have pressure to the power of 4, right? Why power 4? Because we have 3 and 1, right? So that would be 1 over p squared, which is pressure to the power of minus 2, right? So this is going to be atmosphere minus 2. Equilibrium mixture D is made when 1 mole of nitrogen and 3 moles of hydrogen gas are added to a sealed container at 750 degrees Celsius and 1000 atmospheres and left to reach equilibrium. This mixture contains 1.16 moles of ammonia. So this is at equilibrium. This is at equilibrium. Calculate the mole fraction of ammonia. Okay. So mole fraction is the moles of ammonia over the total moles of gas present, right? Mole fraction is moles over total moles, right? We need to find the total moles. We know the moles of ammonia at equilibrium, okay? So again, we can just use an ICE table, okay? So we have N2 plus 3H2 gives you 2NH3. I have deliberately chosen papers with equilibria questions as well. That's one of the things I wanted to see because that's the thing we did at the end. So उसकी भी practice हो जाएगी आप लोगों की. So we have initial, change, equilibrium. Again, I stands for the initial amount, the change, and the equilibrium amount. The initial amount of ammonia, of nitrogen is 1 mole, right? We have 1 mole of nitrogen to begin with. We have 3 moles of hydrogen to begin with, right? And initially we just mix these two together, okay? So it's made when these two are mixed or they're added to a sealed container. So that's your initial amounts. Initially you have 0 moles of ammonia, and at equilibrium you have 1.16 moles of ammonia. At equilibrium, you have 1.16 moles of ammonia, right? That's given to us at the end. So that means how much was produced? That's the change. Change is positive, right? Why is it positive? Because we're making ammonia, right? It's increasing, the positive change, going from 0 to 1.16. Okay. So increase is plus 1.16. That means the decrease in nitrogen is half of this. Why? Because you have a 1 to 2 ratio. If 1.16 of this are produced, then half the number of moles of nitrogen are reacting, right? Just divide by 2, right? So how much is reacting of nitrogen? Minus 0.58. Okay, so minus 0.58 moles so the change for nitrogen is minus 0.58, right? This is the number of moles that are reacting. So we have 1 minus 0.58, which is 0.42 moles at equilibrium. right? And then for hydrogen, you have a 1-to-3 ratio. So if 0.58 of this are reacting, you have 3 times the number of moles of hydrogen reacting, right? So then that would be 1.74. So minus 1.74, that's the moles that are reacting. Again, negative because they're decreasing, they're reacting. And you get 1.26, right? So those are your moles, right? Those are your moles. This is, I've done all the calculation in moles. Again, you can use concentrations directly if concentrations are given, okay? Yeah, either way is fine. You can also use moles of ammonia to calculate this. It'll just be 3/2 times 1.16. It's the same thing. It'll give you 1.74. And then your moles of ammonia is 1.16. Okay, so we have to find the mole fraction of ammonia is moles of ammonia, which is 1.16, divided by total moles. Just add these together, right? Let me just put them in a single denominator like this. Right, 1.16 divided by 0.42 plus 1.26 plus 1.16. So that would be 1.26 plus 0.42 plus 1.16. That gives you 2.84. Okay, and then you do 1.16 divided by 2.84. 1.16 divided by that would give me 0.408 as the mole fraction of ammonia. The mole fraction obviously always has to be lesser than 1, right? Or less than or equal to 1. Lesser than 1 if you have uh, more than one thing. So it'll always be less than 1. And then the mole fraction of nitrogen gas is 0.625 in a new equilibrium, mixture E. Calculate the partial pressure of nitrogen when the total pressure is 1,000 atmospheres. This one's also pretty straightforward. The partial pressure of a gas is the mole fraction times the total pressure. Okay. Again, X just stands for mole fraction. So the mole fraction is 0.625 times the total pressure, which is 1,000. That gives you 625 atmospheres. I think this is a pretty easy paper so far. Pretty straightforward comparatively compared to the harder ones. When oxides of nitrogen escape into the atmosphere, they may be involved in formation of acid rain from sulfur dioxide or the formation of photochemical smog. Identify the role of NO and NO2 in the formation of H2SO4 from SO2 in the atmosphere to produce acid rain, right? So oxides of nitrogen, NO and NO2 are catalysts, right? They are catalysts, right? And they, I'll also write this in brackets, right? They catalyze the formation of sulfur trioxide. Okay, they catalyze the formation of SO3, right? Now we have to write equations for this. Okay, now because they're saying NO or NO2, you can start with any one of them. Okay, nitrogen, let's just start with nitrogen dioxide. Nitrogen dioxide reacts with SO2 to form NO plus SO3, right? Now, normally sulfur dioxide doesn't react with oxygen to form SO3 in the absence of a catalyst, okay? But when you have a catalyst, you have a lower activation energy. So this reaction has a much, this reaction has a lower activation energy than the reaction with oxygen, okay? Sulfur dioxide doesn't react with oxygen, but it does react with NO2 to form SO3, okay? And then your nitrogen monoxide can react with oxygen to form NO2, okay? Nitrogen monoxide can react with oxygen to form NO2. Okay, the overall equation here, okay, the overall equation here is, let me write that down, half O2, right? The overall equation is on the left and right, NO2 cancel out, right? And then NO also cancels out, right? So here NO2 is a catalyst. NO2 is a catalyst, is used at the start and then regenerated at the end. right? So overall equation doesn't show up, right? Because if you add the left and right hand sides up, the NO2 cancels out. And then the NO also cancels out. NO is called an intermediate. An intermediate is something that's made during the reaction and then used up. It's made and then used up. Okay, it's made in the first step, used up in the second step. The overall equation that you get is SO2 plus half O2 gives you SO3. Okay, so you made sulfur trioxide, and then this sulfur trioxide can react with water to produce sulfuric acid, right? An acid rain. If you reverse these two equations, that's also fine, because they're saying you can use any one of them as a catalyst. So in the equations I've shown, NO2 is a catalyst, right? It's being used up and then regenerated at the end. So it's not used up at the end, right? It's used and then regenerated. If you reverse the equations, then that would be NO as a catalyst. So write this equation first and then this equation second, right? You'd get the same overall equation. All right, so this is your acid rain. Right, this is acid rain. Okay, so that's how you can produce sulfuric acid. Okay. Outline how NO and NO2 may contribute to the formation of photochemical smog. You guys should just know this, that they can react with. What do they react with? Unburned hydrocarbons. They can react with unburned hydrocarbons. Okay, to form PAN. To form PAN. PAN stands for peroxyacetyl nitrate. If you don't know the full name, you can just say PAN. Okay, that basically contributes to photochemical smog. Write an equation to show the reaction with a standard enthalpy change of formation of H2O. Include state symbols. Standard enthalpy change of formation means 1 mole of H2O being produced from the elements in their standard state. We're going to have H2O liquid, and we're going to have 1 mole of this. Okay, you have to show 1 mole in the equation, because when you make enthalpy of formation, by definition, is when you make 1 mole of something, right? When you make 1 mole of something, 1 mole of a substance in its standard state, that's liquid, from the elements in their standard states under standard conditions, right? So what are the elements here? You have 1 H2O, you'll have 1 mole of H2 gas, and you'll have half a mole of O2 gas, right? You'll have half a mole of O2 gas. Water is one of the products in the reaction of B2O3 and ammonia as shown. Table 3.1 shows information about the standard enthalpy of formation of some substances. Calculate the enthalpy change for reaction 2 using the data from table 3.1. To determine what to use, just look at the data given. The data given to us is enthalpy of formation. You can draw an energy cycle, we don't have to. Okay, if you draw the energy cycle, you would have B2O3 plus 2NH3, right? That would be one box. Then you have 2BN plus 3H2O, right? That would be another box. And then you would have elements over here. Why would we have elements here? Because enthalpy of formation is given to us. Again, you have to look at the data given to determine what cycle to make, right? And then this would be formation of B2O3. This would be 2 times formation of ammonia, because you have 2 moles. This would be 2 times formation of BN and 2 times formation of water, right? So you can draw the cycle and calculate it, right? You can say this plus this is equal to this, right? But we don't have to draw the cycle here. You can just use the formula. The enthalpy change of a reaction, if the formation data is given, is formation of products minus the formation of reactants. Okay, formation of products minus formation of reactants. So then the products here are Bn. We have 2 moles of that. So 2 times minus 134 plus we have 3 moles of water. So that would be 3 times minus 286. And then you're going to subtract all the reactants. We have 2 moles of ammonia, so minus 2 times minus 46. And then you have 1 mole of B2O3, so you're going to minus that. So minus 1264. Okay. You subtract the values given, and then you get positive 230 kilojoules per mole. Okay, so the answer is positive 230. You can just say 230 as well. I always include a sign because in some cases they do require it. Okay. You don't have to draw the boxes, no. When you're drawing the energy cycle, you do not have to draw the boxes. You can draw it without the boxes as well. I don't usually draw the boxes the way I taught it in class, right? Boron carbide is a hard crystalline solid that has a melting point greater than 2000 degrees Celsius. Suggest the structure and bonding in boron carbide. Well, boron and carbon are next to each other in the periodic table, right? So they don't have a very large difference in electronegativity, so it won't be ionic. So then what type of a compound would it be if it's not ionic, that has a very high melting point? It would be a giant covalent structure, yes. Giant covalent, right? Lattice. Okay. Then you have 100 grams of pure 100 grams of pure boron carbide contains 78.26 grams of boron. Calculate the empirical formula. We've got boron and we've got carbon, right? We know it's carbon because the name carbide, right? So we've got the masses given to us, right? We're gonna do, okay, if you have 100 grams, we have 78.26 grams of boron, 78.26, and then you can just do 100 minus that would give you 21.74 grams of carbon. Then you have to divide by the atomic masses to find the moles, right? So the atomic mass of boron from the periodic table is 10.8 and carbon is 12.0. So we're going to say divided by 10.8, divide this by 12.0. You get the mole ratio. So you get 78.26 divided by 10.8. That gives you 7.25 moles of boron. And then you have 21.74 divided by 12.0, which gives you 1.81 moles of carbon. And then just divide by the smallest number. So you get roughly 4:1. So then the empirical formula is B4C. Okay. Or you can say CB4, same thing. That's boron carbide. NH3 reacts with HCl gas to produce NH4Cl solid as shown. Draw a diagram to show the ionic, covalent, and coordinate bonding present in a formula unit. We have to show the ionic, covalent, and coordinate bonding, okay, in a unit of NH4Cl. Now, NH4Cl consists of the NH4 plus and the Cl minus ion, right? So what do we have? First, we're going to draw NH4 plus. So we've got a nitrogen. Initially, we had ammonia, right? We have to show the coordinate bond. Coordinate bond is the dative bond. If you guys remember, nitrogen will form a dative bond with H plus, right? Nitrogen will form a dative bond with H plus. So you don't have to show the lone pair. I always like to show the lone pair. You have to show the arrow. Remember, if they ask you to show a coordinate bond, you have to show the arrow, okay, to this hydrogen. Overall charge is 1 plus, right? That's the ammonium ion. And then you have Cl minus, right? So you've got ionic between this cation and anion. You've got regular covalent bonds, and then you also got the coordinate bond. You do not have to show the no, you do not have to show the bond angles. You don't have to show it as tetrahedral. No, that's not the question it's asking. It doesn't say you have to show the shape. Okay, it is not asking you to show the shape. It is just asking you to show the bonding. Okay. An exothermic reaction occurs when ammonium is added to hydroxide. Identify the type of reaction. Ammonium is a acid, right? It's a proton donor. Hydroxide is a base. It's an acid-base reaction. We don't normally say neutralization because neutralization, specifically whenever we say neutralization, we're talking about this reaction. Although technically this is accurate as well, because ammonium does give H plus ions in solution which react with the hydroxide, but we'll just go with acid base and then construct an ionic equation. If you're unsure, you can just write both. So construct an ionic equation for the reaction of ammonium and hydroxide. So we have NH4 plus OH minus gives you NH3 plus H2O. Okay, right? This is a test for the hydroxide ion or test for ammonium ions as well, right? Hydroxide, it produces a colorless gas that turns damp red litmus paper blue, right? That's ammonia. Substitution reactions of ammonia and hydroxide with halogenoalkanes both involve a lone pair of electrons. Name the role of ammonia and hydroxide in these reactions. Halogenoalkanes undergo nucleophilic substitution. They undergo nucleophilic substitution, right? These are called nucleophiles. Nucleophiles are species that donate a pair of electrons, right? So these are nucleophiles. Suggest which species is more reactive. Explain your answer. Well, I would say the hydroxide definitely would be more reactive. There's one obvious reason. Not the, yeah, more lone pairs is not the best reason to give. There's two obvious reasons why it's more reactive. First of all, it's negatively charged. Ammonia, nitrogen has a partial negative. Secondly, oxygen is a more electronegative atom anyways than nitrogen, right? So both of those things would explain why hydroxide is more reactive, right? So hydroxide, because it has a negative charge, right? Right. Whereas, uh, hence, it is more strongly attracted to the carbon delta plus or the positively charged carbon, right? Depending on the mechanism. If you guys remember, in nucleophilic substitution, right, we have a carbon that's partially positive because and the hydroxide will attack that carbon, right? Now it could be partially positive or you could get a carbocation, in which case the carbon is fully positive, right? So either one. Okay. It's a better nucleophile. When 2-bromo-2-methylpropane reacts with hydroxide, two mechanisms SN1 and SN2 both occur, right? SN1 is the two-step mechanism, right, in which you get a carbocation. This is a tertiary halogenoalkane. Let me draw this out. We have propane. Propane means we have a 3-carbon chain, right? Propane means we have a 3-carbon chain. We have a methyl on carbon 2 and a bromine, right? This is 2-bromo-2-methylpropane. So look at the halogenoalkane. This carbon, the carbon with the halogen, this is the carbon with the halogen, right? Is bonded to 3 carbons. Is bonded to 3 carbons. That makes it a tertiary halogenoalkane. Tertiary halogenoalkanes favor SN1, right? Tertiary halogenoalkanes favor SN1. Why? Because you get a tertiary carbocation, which is more stable due to the positive inductive effect of the alkyl groups, right? So the intermediate here would be a tertiary carbocation. Okay. Complete figure 4.2. Oh, first it says sketch a graph to show the reaction pathway for the SN2 mechanism. Now the SN2 mechanism has a slower rate, obviously, because tertiary halogen alkanes favor SN1. So SN2 would have a higher activation energy, and it's a one-step mechanism. SN2 is a one-step mechanism. Just remember that, right? So this is what it would look like. Okay. The overall enthalpy change would be the same because you have the same reactants and same products, but much higher activation energy, right? And why do tertiary halogenoalkanes not favor SN2? Because SN2 mein what happens? SN2 mein the hydroxide attacks the carbon directly and then the CBr bond breaks. But there's not enough space. There's not enough space for the hydroxide to attack the carbon because of these methyl groups. That's called steric hindrance. That is called steric hindrance. Okay. It literally just means the restriction of physical space. There's space is physically restricted because of all the alkyl groups. Okay. That's why tertiary halogenalkanes don't undergo SN2 or barely undergo SN2. Okay. Complete figure 4.2 to show the mechanism for the SN1 reaction that occurs when this halogenoalkane reacts with ammonia to produce this product. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Now they've already pre-drawn a lot of the stuff for you. So they've shown you that you're getting a carbocation, which means in the first step you have heterolysis. Heterolysis is when this bond breaks and both the electrons go to one atom. That would be the bromine, right? You have put the partial charge. You have bromine is partially negative, carbon is partially positive. Okay. Then you have this carbocation form, and then in the second step, your nucleophile comes in, which is ammonia. Right? Ammonia is your nucleophile. Again, that's given to you, right? Pretty obvious. So then we have, again, lone pair. From the lone pair to the positively charged carbon. Okay. Curly arrow from the lone pair. You have to show the lone pair. Okay. You can write ammonia like this. It doesn't matter. It's the same thing. Okay. And you get this. And now for the last bit, okay, I want to mention this that it's a bit inconsistent, okay, the mark schemes for these, and if you look at questions from other papers as well, right? I mentioned in class that you're going to get H and then Br, so HBr, right? So sometimes we just show the Br minus taking the hydrogen away, but this is not what actually happens, because what happens is that HBr is you have ammonia present in excess. So ammonia reacts with HBr to form ammonium bromide, right? So what's actually happening is that this hydrogen is not taken away by the bromide, because bromide is not a very strong base. Okay, it's not very good at accepting hydrogens. Ammonia is a better base. So the better way to show this would be like this. Okay, the better way to show this would be that the ammonia takes the hydrogen like that. Okay, the ammonia takes the hydrogen. Okay, why do we know? We know that there's a loss of hydrogen because we have an NH2 here. We have an NH3 over here, which means that one of the hydrogens is being taken away. And that would be the ammonia that takes away the hydrogen, and this bond breaks. Okay. As I said, the exams are inconsistent with this. Often, sometimes you'll also see HBr written as the product, but the final product is ammonium, right? Because H and NH3 give you ammonium, and then you also have Br minus, right? That's ammonium bromide. Okay. In this particular question, they expect you to say this because they've also given this earlier on. They said that you get ammonium, right, with the HBr. So they expect you to figure that out from the context in the question anyways. But yes, that's the proper mechanism. Okay. The proper mechanism is that if you have a halogenoalkane, it reacts with ammonia, right? You get R NH2. The halogen is substituted by an NH2, and then you get NH4Br. Okay, you get NH4Br. So you'll have 2 moles of NH3. 1 mole of NH3 at the start, or 1 NH3 at the start, and then 1 NH3 at the end to take away the hydrogen. Yes, just always show it this way with ammonia. I did mention it, I think, in one of the classes, one of the lessons at school as well. Who brought it up? I think Momin brought it up. Is Momin here? Momin, are you here? Momin is MIA. Maybe. I have no idea. Identify the inorganic product that forms. That would be NH4Br, right? Ammonium bromide, what I just told you. Okay, and then give the systematic name for this product. Give the systematic name for this product. Okay, so we have this product right here. Your longest carbon chain is C2. I hate it when they write C2H5. It should be CH2, CH2, CH3. You got 1, 2, 3, 4 carbon chain, right? That's the longest chain. So 4 carbon chain would be bute. Carbon-carbon bonds are all single bonds. So AN. And then you got an NH2 group on carbon number 2. Okay. You're going to number the chain. You're going to number the chain from here because you want the lowest number for the functional group. So you got bute, AN because single bonds, and then 2, and then amine. Okay, that's the proper name, butane 2 amine. Okay, butane 2 amine. Right, we drop the E. We don't say butane because this is a vowel, right? So butane 2 amine. All right. Complete the table by drawing the structural formula of the intermediate that is formed when 2-bromo, 2-methylpropane reacts in an SN1 reaction. 2-bromo, 2-methylpropane. Okay. So 2-bromo, 2-methylpropane, I've drawn it right here, right? The carbocation will be then the bromine is lost, right? So you have a carbon with 3 methyl groups. I'll draw it again, okay? We've got 2-bromo, 2-methylpropane. So that would be a 3-carbon chain, 3-carbon chain propane, right? And then on carbon number 2, you have a bromine and a methyl. So you have a CH3, CH3 here. You have a CH3 over here. And then you also have a bromine, right? But in the SN1 mechanism, the bromine is lost in the first step, right? So you end up with a carbocation intermediate. Okay. So you can draw the plus. I'm just drawing it the way they've drawn it. You can draw it here as well. It's the same thing. Okay. Identify the halogenoalkane that has a greater tendency using the SN1. Which of these carbocations is more likely to form? SN1 mechanism forms carbocations. This is a tertiary carbocation. The carbon with the positive charge is bonded to 3 carbons. Whereas this is a secondary carbocation because the carbon with the positive charge is bonded directly to 2 carbons, right? You have 1 hydrogen. So we can say which of these halogenoalkanes there will be 2-bromo, 2-methylpropane. 2-bromo, 2-methylpropane has a greater tendency. Why? Because it forms a tertiary carbocation intermediate, right? Okay. Which is more stable, which is more stable than the secondary, right? Secondary would be 2 degree, right? You can also say 2 degree or secondary, either way is fine. Then the secondary carbocation intermediate. Again, more stable simply means that it's at a lower energy, so a lower activation energy is needed to make it, okay? I'll write this down in brackets, okay? Lower activation energy is needed for tertiary. So then the secondary carbocation intermediate, right? That 2-bromobutane forms, right? Right? And why is it more stable? Due to the positive inductive or electron donating effect of the alkyl groups. Due to the positive inductive effect. alkyl groups. Alkyl groups. M reacts to form R by the addition of one reagent as shown in figure 5.1. Identify the reagent and conditions for this reaction. So alkene is producing a diol. NH3 will be an excess here, yes. Yes. So this is a weak oxidation of alkenes. Okay, weak oxidation of alkenes is when you add two OH groups. When you add two OH groups, right, to the double bonded carbons. So this, for this, the reagents are cold, dilute, acidified, KMNO4. Okay, all of it is required: cold, dilute, and acidified. Okay, KMNO4, MNO4 minus, manganate 7, right? You can say H plus slash MNO4 minus, or you can say KMNO4, same thing. R is also made from M by two steps. The first step is we're adding two bromine atoms, and then we're replacing the bromines with OH. Okay, so step one, when you're adding bromine, you can just use aqueous bromine, right? You have to identify the reagents and conditions. Okay, so we're going to use the reagents are Br2. Okay, it can be liquid, it can be aqueous. Okay, liquid is preferred. Okay, because you get a higher yield of the desired product. So you can use bromine. Okay, and if you want to be even more specific, right, it would be in the absence of light. Okay, that's an optional condition where you can mention it, right? It's at room temperature in the dark. Why in the dark? Because in the presence of UV light, you can get substitution as well, right? So that's why they say in the dark in brackets. Okay, and then if you want to convert a halogenoalkane to an alcohol, right, that's called hydrolysis of halogenoalkanes. You have to use sodium hydroxide aqueous. Do not just say sodium hydroxide. In this case, aqueous is required. In this case, aqueous is required. Okay, because sodium hydroxide and ethanol results in elimination, right? You get an alkene. These two are removed, and this and here, this is also removed, right? You get an alkene. So it has to be sodium hydroxide aqueous. Okay, NaOH aqueous. Okay, and heat. Okay. Name the mechanism for step one. That's just electrophilic addition. Yes. And then the mechanism for step two is nucleophilic substitution, right? The infrared spectrum of R is shown in figure 5.3. Okay, R. R is this guy, right, with the two OH groups. Use the absorption in the region above 1500. So again, we're looking at only the fingerprint. We're looking beyond the fingerprint region, right? The region below 1500 is the fingerprint region. So we're only looking at this region over here, right, to the left of the 1500. Again, we read this graph from left to right, from right to left, sorry. So we're looking to the left of 1500, okay? Add F to figure 5.3 to identify, add F to figure 5.3 to identify the peak. So we have to label the peak F, right? And then we also we have to identify the bond that's responsible for that peak. Okay. So both Q and R have the CH bond, right? They both have the CH bond, which is going to be this one, right? This is around 2850 to 2950, right? Around 2900, roughly. So this is bond F. This is peak F, right? And this corresponds to the CH bond. And then add G to identify the peak that is not present in Q. Okay, that is not present in an infrared spectrum of Q. Q is So halogenoalkane, right? This is an alcohol. Alcohols have the OH bond, right? Alcohol have the OH bond, right? So this is your label G, right? The OH bond is 3200 to 3650, right? In the hydroxy. You also have C single bond O, but that's not above 1500. We're only looking at above 1500. So we're looking at the OH bond, right? Present in R, but not in Q. Okay, so that is the OH bond, right? And Y is made from Q in a three-step reaction. The first reaction, you're using KCN and ethanol. KCN and ethanol is when you substitute a bromine with a cyanide, right? You get a nitrile. You get a nitrile, right? And that nitrile can then be converted to a carboxylic acid, okay, by hydrolysis. So the first step is nucleophilic. So I'll just draw W, right? What do we have? We got this, and then we got nitrogen. We got nitrogen, right? Again, this is C triple bond N, right? I'm just drawing skeletal because why not? Because I can. Okay, and then right, these nitriles are converted to carboxylic acids, right? The significance of this reaction is that it can increase the number of carbon atoms. Okay. In step 2, this compound is heated with with an acid, dilute HCl, to produce a carboxylic acid, right? A diacid specifically, and an inorganic product. This is acidic hydrolysis. Acidic hydrolysis of nitriles. Now, if you guys remember acidic hydrolysis of nitriles, right? Acidic conditions, now what do you get? You get the this carbon is converted to a carboxylic acid, right? And then the nitrogen is converted to ammonia, right? Because hydrolysis, what happens? The C triple bond N breaks. The C triple bond N breaks, nitrogen forms ammonia, but in acidic conditions, it will form ammonium. In acidic conditions, it will form ammonium. So NH4 plus, right? Since you have H plus, you can also say plus Cl minus, right? Since you have HCl, right, you would say NH4 Cl, right? NH4Cl. So that's the inorganic product. Okay, ammonium chloride. Okay. They say identify the formula. So that would be incorrect to name it. Be NH4Cl. In step 3, X reacts with reducing agent Z to produce Y. So the reducing agent is Z to produce Y. What's happening here is that a carboxylic acid is being reduced to a primary alcohol. Why chloride? Because you have HCl. So instead of H plus, you would have Cl, right? Right? H plus नहीं लिखा, HCl. So ammonium chloride. Yeah. All right. So when we talk about carboxylic acids to primary alcohol, that's reduction of carboxylic acids. Okay, reduction of carboxylic acids. And carboxylic acids can only be reduced using lithium aluminum hydride. Okay, lithium aluminum hydride. So, okay, the reducing agent is lithium aluminum hydride. Okay, it has to be anhydrous. Okay, it has to be anhydrous. So the solvent that we use is ether, lithium aluminum hydride, and dry ether. Okay, that's the solvent. It cannot be aqueous. Okay, the other reducing agent that we've learned about is NaBH4, but that does not reduce carboxylic acid. That only works on carbonyl compounds, aldehydes and ketones, whereas LiAlH4 works on both. Okay, so first let's look at the reaction. Right now, how many hydrogens are we adding? We're making a CH2 here. We're making a CH2 here. So that's 4 hydrogens, right? And then we're taking away 2 oxygens. We're taking away 2 oxygens, so we're making 2 H2O as well, right? We're making 2 H2O. That's 4 more hydrogens. That's 4 more hydrogens because you need 2 hydrogens to take away 1 oxygen, 2 hydrogens to take away another oxygen. You guys should know this equation from before. COOH reacts with 4 hydrogens to form CH2OH, okay, plus H2O. So one carboxyl group needs 4 hydrogens from the reducing agent, right? two hydrogens add on, you increase the number of hydrogens, and then two hydrogens take away the oxygen. Two hydrogens take away the oxygen. So you need four hydrogens for one carboxyl group. If you have two carboxyl groups, you're going to need eight hydrogens. Okay. You have two carboxyl groups, you're going to need eight hydrogens. Okay. And then what are we going to get? We're going to get C8H. Again, we're adding two hydrogens here and two hydrogens here, CH2 and then CH2, right? So we're going to have H16. Okay. H16 and then O4, and then we're going to get 2H2O. Okay, again, every carboxyl group will give you one H2O. So we're going to get 2H2O. Okay, and then Z is lithium aluminum hydride, right? That's your reducing agent. Okay, I'll write that in brackets. Okay, it has to be in dry ether, or you can say anhydrous.